Okay. Some limitations of calorimetry, like I said, it's not going to work for all reactions. Okay. Okay. First of all, and reactions have to be fast. Why? Well, if it takes 1,000,000 years for the reaction to happen, you can't do it in the lab, right? So it has to be fast, and also, even if it doesn't take 1,000,000 years, let's say it just takes days, then that's still going to be a problem because it's very hard to maintain perfect insulation. Okay, so you don't want to have to worry about that heat loss. So you want to make sure your reactions are fast. Reactions must be complete. That means your limiting reactant has to be consumed completely. Otherwise, you wouldn't know how much reaction actually happened, right? You have to do an extra step to figure out what else, how much product did you make, how much reactant did you consume, and more importantly, that Q for the unmixing, that last step we talked about earlier, will not be equal to 0 if it doesn't go to completion. Okay, so you cannot equate your heat of reaction to either delta H or delta E. So another condition is there must be no side reactions. Well, because if there's side reactions, then you wouldn't know what that overall heat measurement you made is related to. How much of it is due to this reaction? How much of it is due to the side reaction? So these are some of the limitations of calorimetry. It's not suitable for every reaction. So what do we do? If a reaction is not suitable for calorimetry, we have to use our imagination. Okay? We take advantage of the fact that H is a state function. We use what's called Hess's Law. Hess's Law, like I said, Hess's Law basically says that if the delta H for a reaction cannot be determined by calorimetry, you can imagine a series of reactions that will eventually convert your reactants to your desired products, and simply add up the delta H for all of those steps. So this is the significance of defining of H, okay? Because H is a state function. If there is a reaction for which you do not know, you cannot measure delta H directly. You can try to figure it out in terms of other reactants that you can measure, other reactions that you can measure. Okay? So since H is a state function, you can do that. And if you know the reverse of a reaction, if you can measure the delta H for the reverse of a reaction, that's just the negative of the delta H for the forward reaction. Okay? So if going from A to B generates 5 joules of heat, then you would expect going from B to A to absorb 5 joules of heat. Okay? So those are consequences of H being a state function. So also, if H is an extensive property, it's proportional to the amounts of reactants involved in the delta H will be proportional to the amounts of reactants and products involved in the reaction. So you use twice as many reactants, you consume twice as many reactants, then that means your delta H will be twice as much. So if you adjust your coefficients in your balance equation, you can do the same adjustment to your delta H. So let's illustrate that with this example, a few simple examples here. So if A plus B going to C, the delta H is X, what's the delta H for the reverse reaction? Negative X. Okay, so for example, if X going to Y, delta H is equal to negative 3 kilojoules, what's delta H for Y going to X? Negative of negative 3, which is positive 3 kilojoules. So you reverse a reaction. So if you could measure this, okay, and you could not measure this, it doesn't matter. If you can measure this, all I have to do is imagine flipping it, and I just get the opposite delta H. Okay. How about this one? A plus B gives you C, and delta H for that reaction happens to be, let's say, X. Well, if I change my coefficients to 3, 3, and 3, what would be my delta H? 3X. Okay. If 1 mole and 1 mole to give you 1 mole gives you X, then if I triple the amounts, 3 moles instead of 1 mole, I triple the delta H. How about this one? A plus B gives you C, delta H is X. What would be the delta H for this reaction right here? Negative X, negative 2X. Why negative 2X? Because I flipped it when I flip it, it becomes, so if I just say C gives you A plus B, delta H would be negative X, right? But here, not only did I flip it, after I flipped it, I multiplied all the coefficients by 2. So delta H for this would be negative 2X. How about this one? A plus B gives you C, and then C gives you D plus E. Delta H for this step right here is X. Delta H for this second reaction is Y. What's the delta H for this reaction down here? What happened here? A plus B became C, and then C eventually became D plus E. Right? So A plus B eventually becomes D plus E. So you can imagine this as occurring as a series of two steps. The first step, A plus B first turned to C, and then C turned to D plus E. So what's the delta H for this one? It's just going to be X plus Y. That's what Hess's law is all about. Okay?